So this week we will talk about weighted least squares. Let me start the slideshow. Okay, so previously we have talked about simple linear regression where we regress y on x, and also we talked about diagnostics and transformations, etc. And this week's lecture is following the transformations that we discussed the last week, where we have to transform y when we have non-constant error variance, or we transform both x and y, etc. just for the problem of non-constant error variance. So this weighted least squares is just the alternative way to address that problem. So again, in this weighted least squares, we are still building a straight line regression model. So it's still a linear regression model, but we are incorporating the weights in order to account for the differences in the error variance. You will see that soon. So now let's look at the model. We have our classic linear regression model like this, where we have this old assumption that our error have mean 0 and constant variance sigma square. Now we have already identified we have the problem of non-constant variance of the error. So we have this new assumption, this EI, our error has mean 0, and now we use a weight for the error variance. So it's now sigma square over this WI. This WI is the weight that we put on the new error variance. So this is our new assumption. Again, so for this weight WI, when it's large, that means because it's in the denominator, it's large, that means the error variance is small, it's close to 0. And the points are closer to our fitted line. So the variance, it's smaller. I'm going to add the following information where I forgot. Sorry about that. So our parameter estimate in this case, when we have a large weight, we estimate our beta 0 and beta 1. So now the fitted line at x would be close to y. That's what I mean by the points are close to the fitted line. And we are taking the i's case into more account, take more into account. Because it has a large weight. So when the weight is small, again, as a denominator, when we have a small denominator, the whole variance sigma square over WI is large. So when we fit the model, get our parameter estimate, then when we do the estimation, we do not really take this points into account as much because it has a smaller weight. And so this is the the background kind of information when we have a large or small weight for each our case. So okay, let's look at how are we going to do the estimation when we have this weight incorporated in the model. So again, we will use this weighted residual sum square. So previously we have RSS, which is just the residual sum of squares. Now we have the weights incorporated, so it's weighted RSS. And it can be written as a summation of weighted sum of squares, weighted squares, and then sum them up, right? And then write this y wi hat out by this it's, yeah, you can just write like this. And in matrix format, it's now being y minus x beta transpose times w, where this w is the weight matrix, and times this y minus x beta, where previously we do not have this w in between of these two, right? Well, yeah, I think this is right. There's no problem. Oh, by the way, this W here is a diagonal matrix with all the weights on the diagonal. So for each weight for a corresponding observation, you will have the Wi on its corresponding diagonal value for that matrix. So again, the larger our weight is, the more that we take this i's case into account when we fit the model. And now we can try to find our beta 0 hat and beta 1 hat that minimize this weighted residual Simon squares. So, so that's our weighted least squares estimate. Let's look at how do we do the calculation. It's very similar as before. We set the derivative with respect to beta 0 and beta 1. Sorry, I should put this beta 1. Set the derivative both to 0 and solve for this beta 0 and beta 1. So we rearrange this like this to put beta 0 and beta 1 on the right-hand side. And now we can solve it. You can verify this. It should have no problem, but I just need to correct this to be B1 instead of B0. Okay, so now we get our beta 1 hat. So just to clarify, when I put this B0 and B1, that means they are the true parameter that we're trying to find. And once we get solve those equations, we get our estimate. Now I use this beta 1 W, beta 1 hat W. So that's for the weighted least square estimate. So it looks like this. If you solve the previous two equations, and now our x bar W and y bar W are the weighted means. It looks like this. So it just as it sounds, it's weighted means after you take the weight and you take the mean, right? This is weighted sum of this xi, and you divide it by the summation of your weights. And similarly as here. And with this information, we find that beta 0 hat, weighted beta 0 hat, equal to this yw bar minus this beta 1 hat. Oh, I should put this w here, which this one is just this one, times this x bar w. So basically this our estimated slope would equal to the weighted mean of y minus our weighted slope, weighted estimate slope, times the weighted mean of x. Okay, I put everything in matrix format because, well, some people might find this is a bit messy, and especially, yeah, if you do more theoretical kind of study, you might prefer this notation that you put everything in matrix and vector format. So again, we just do the derivative for this matrix multiplication, again, refer back to the very beginning that when we have the prerequisite for the matrix operation, algebras. So you can find this, this is how should you calculate the derivative. And again, we set this to 0 in order to find our beta hat, the weighted least square estimate. And I want you to pay attention. This weighted least square estimate is very much similar as before when we do not have this weight in the middle. So right, our original beta hat is just x prime x. You take the inverse and then times x prime y. So just want to show you the difference, and it's much easier to remember, right? Comparing to like such complicated formulas here. Let's go to an example where this is actually kind of a special case. Remember, we have worked on an example where we have x being the number of proofs and y being the number of rooms cleaned, and we have like multiple days being being those multiple points for each distinct value of the cruise on the x-axis. So now we have multiple measurements at each value of x. So that means we can get the standard deviation for each different value of for each xi. I should say at each x value we can get the variance or the standard deviation for this group of points, and also for this when number of crews equal to 4, we can get the corresponding standard deviation or the variance for this group of data points, etc. And now we can get this table here for each distinct number of crews, and we have, this is the total number of points that we have for this value. Now we can get the standard deviation of yi. So yeah, in this special case, we can measure the standard deviation at each xi value. That's the standard deviation of yi. Oh, sorry about all these typos. I should read it more than one time to avoid these typos for next time. Okay, now we know we can get our standard deviation for the y, and we can get the standard deviation of the variance of y. Now we know how we should like trying to figure out what should we use for this wi, right? So now, yeah, let's just recap here. Now we're assuming this EI has mean 0 and variance being the sigma square over WI. Now we need to find what should we use for this WI. Remember our objective here is trying to make the variance constant, because we had the problem of non-constant error variance. Now we try to make them equal. So here we choose that WI being 1 over the variance of YI. So that this sigma square over this WI would be kind of constant. They are more or less equal for different EI. Let's take a look at how do we do this with R. So this is how we, well, actually I have this in our lab. Let me see, yeah. Let's just go directly to our lab session here. Yeah. Oops. So, let's just run it line by line, even though I have run them this, which is Control R, clear it up, and let's rerun it again. Set my working directory to where my data is saved. And now read my data in. And now the data is like, we have another column. We have another column here called standard deviation. We're going to use this later. So previously, this is our regular linear regression model, and this is what it is. Do the cleaning. Oh yeah, this. This is only regress this number of rooms on the number of crew. And now we do this weighted least square model, where if you pay attention, I put this weights equal to 1 over this the square, the standard deviation, which is the variance of y at different value of x. So if we plot, well, I have this plotted already, but let me redo it. So this is the plot of the data, and if we add the line to it from our weighted least square model, looks good, right? And if we do a summary, and this is what I had in our slides, where the summary showed the estimate has changed from the original one, where originally if we don't do any weighted least square, we have this kind of 1.8 and 3.7 being the estimate. But now for the weighted least square, it has slightly different estimates, right? Well, I provide here an alternative way that you can do this weighted least square, where you manually add the weight to your variable. So so here for y value divided by the standard deviation of y, and for, yeah, so this is your new transformed y, and this is your new transformed x value, where divided by the standard deviation. Notice the standard deviation here no longer is not a variance. Where we specify the weights for this LM function, you would use the standard deviation to square the standard deviation, where it's the variance. Pay attention here. I also put the kind of transformed our intercept, right? So, and for all the operations that I do for these variables, I have to use this I in order to make this LM function to recognize this is your new transformed variable. So if you do it this way, where I'm -1 here, that's a minor than the original like intercept. Originally it would have an intercept, but now I want to remove it, so I have this -1 here. So if we do this regression and do the summary, you will notice we will have the same estimate as before. Yeah, so this is kind of translates the weight into like the equivalent transformed model we have. Where if there is a caveat here, if you do the plot again with this, when you manually transform your data, And if you add this switch line directly, it would not work. Instead, you should do this. You should do this. Specify this. What is the value for the intercept and for the slope? Yeah, just pay attention. If you prefer do things manually, so that you know what is happening with your variable, but when you do the plots, you have to specify the coefficients from the model.